Hello everyone. In this video, we are going to review some content. It's called the elementary matrix. And no matter you have learned it or not, we are going to do a review and make sure that we're able to continue and know what it is. So the content is copied from Linear Algebra Notebook number 113, and you can find the link below this video. So it says that if A is an n by n matrix, and then we can perform a particular row operations following our notation like this, and to apply it to A and up to 10 A prime. Okay, so if I apply A with this action and to get A prime, then I can apply the same action to identity matrix to get a matrix E. Okay, it seems a little bit fast. Let's look at an example. Okay, so this is the matrix A, this is the matrix B, and B is obtained from A by swapping the rows. So this swapping of rows 1 and 2 also applied to the identity matrix. We choose the same action and apply it to the identity matrix. Okay, and then you will see that, okay, the identity matrix becomes this. And we call this matrix as E. Okay, it turns out that this matrix is called the elementary matrix. It's as simple as that. You pick an action and apply the action to the identity matrix. The resulting matrix E is called the elementary matrix. And the nice thing about this elementary matrix E is that you will see that the identity E times A is equal to A prime, or E times A is equal to B. Okay, so basically this elementary matrix help you to record what you have done to this matrix. If you apply a certain operation to A, then you can just multiply by E to represent this operation. So the other rules also follow the same idea. If you have another rule that you want to rescale the ith row by k, then you rescale the ith row of identity matrix by k. So for example, this row multiplied by 2 becomes this, and this row multiplied by 2 by this. So you apply the same action to the identity matrix, and this matrix is called the elementary matrix. And you can double check that E times A is equal to B. And lastly, you can do the row combination, right? You can use the row 1 and row 2 to combine and make it into a new row 2. Okay, new row 2 is equal to row 2 plus 2 row 1. New row 2 is equal to row 2 plus row 1. Okay, so you get this element. So this new matrix is called the elementary matrix, and you can double check and think about why E times A is equal to B. Okay, so a brief summary. Whenever you do a row operation, you will have a corresponding elementary matrix. And the elementary matrix is obtained from applying this action to the identity matrix. It's as simple as that. Just apply the same action to the identity matrix. So we're going to see some applications of that, but let's try to look at an easy exercise. Okay, what is the inverse of an elementary matrix? The other way to say that is, if you apply an action, how do you apply the other action to get it back? So for example, if you swap two rows, then how do you make the matrix back to the original one? A becomes B by swapping two rows. Then the easiest way is swap the two rows again, then you can make it back to A. So it turns out that if you have an elementary matrix for this swapping, then the inverse of the swapping elementary matrix is again a swapping elementary matrix, and in fact it is just itself. And similarly, you can think about for the other two rules. If you have matrix A and apply the rescaling to B, you multiply a certain row by k. The way to get it back is you multiply the certain row of B by 1 over k and get it back to A. So if you have a rescaling elementary matrix, the opposite or the inverse is again a rescaling matrix, but remember the coefficient will change from k to 1 over k because you want to make it back. Alright, now let's turn to the row combination. The row combination will take one row and multiply by k and add it to the other row. Well, it seems a little bit complicated, but remember that row I does not change here, right? Row j is changed. So how to make row j back to the original one? Just remove the extra k row I, right? If you add k row I to here, then you can remove k row I to get it back. So if you add 2 row 1 to row 2, then the simple way is just take it out, remove 2 row 1 from row 2. So the inverse of that is simply add a negative sign to this extra off-diagonal element. Okay, with these in mind, then we are able to do something interesting. It turns out that every matrix, well, to be more precise, every invertible matrix can be factored into the product of several elementary matrices. So again, this is actually a website, and I will provide the link below, and I will use the seed 2024 to generate this matrix, and it also generates the answer for you. So you are welcome to change the seed and try a different matrix. Okay, so let's try to do the row operation and try to get this back to the identity matrix. This is the matrix A coming from seed 2024. I will apply some row operations, and I do it several things together. So I remove the 4 times row 1 from row 2, remove add 16 times of row 1 to row 3. Okay, so I do that together in order to kill this 4 and minus 16 and get 0 and 0. So now I have this matrix. I want to do further to kill this one. And I have some row operations, and I do some row operations to kill these two and to get to the identity matrix. Well, the interesting thing is that you can get all the thing back and move from elementary identity matrix back to the matrix A. So let's try to do one. The opposite of a row combination is simply plus 2, then you do minus 2, plus 1 you do minus 1, plus 3 you do minus 3, plus 16 you do minus 16, minus 4 plus 4. So now you have several elementary matrices. You know that if you want to apply this action to the identity matrix, then you have to multiply by E5. And what is E5? E5 is simply applying this action to identity matrix, which you can see here. Apply a row combination of adding minus 2 row 3 to row 2, you will get this guy. And once you have done this step, then you want to apply this action. And to apply this action, you multiply by another E4. So you can check that all these things come from each of the actions. Well, so you start from identity and apply E5, E4, E3, E2, and E1, then you get to A. And it turns out that the determinant of A can also be calculated in this way. Just take the product of these determinant. So think about why this formula works, and then go to this website and try another matrix by yourself.